Right? Now we are going to prove the full version of Rados theorem, which characterizes the system of linear homogeneous equations, whether R is regular or not. Okay. Right, and let me remind you the simple version, right? So the simple version was when you have only one equation. So you have one equation, and this is regular if and only if there is some partial sum whose sum of the coefficient is 0. So here we have more general version. So for instance, you have a matrix A. Right. So when is this regular? That's more general, right? And A is an integer valued matrix. So if A has only one row, then that's the previous theorem here. But now we allow A to have many rows. And now let me explain what's called the columns conditions. Here's what it is. We say A satisfies the columns conditions. So A is an integer matrix with n columns. Okay. If there exists a partition I1, I2, IT of integers from 1 up to n into T non-empty sets such that, now here's the important condition. So for each I, the sum of the vectors, okay, so what is Ci? Ci is the ith column. Ith column. Right, the Ci in, let's say in, no, I shouldn't use ij. Right, if I take all the column vectors in II, then this is in the span over the rational coefficients of the set of the vectors Cj, where j belongs to I prime for some I prime less than I. Okay, so that's the condition. So for instance, sum of the vectors in I1 is in the span of some empty set, right? So this has to be 0. Sum of the vectors in I2 is something about, it should be written as a linear combination of vectors in C1, no, I1, and sum of the vectors in I3 is in the linear is in the span of the column span of the column vectors in I1 or I2, right? And CT is in the span of column vectors in the previous ones. All right, so that's what it means. And now you can imagine what the theorem is. So Rados Theorem, which was published in his PhD thesis in 1960s, is that the system AX is 0 is regular on set of positive integers if and only if A satisfies the columns condition. Okay, now when A has only one row, this coincides with the previous characterization, because if A has only one row, then that's it, right? Column vector is nothing but just one integers, right? So this is what it is. Anyway, this is the Rados theorem. Now, it has a number of steps, but the forward direction is easier. So let's prove the forward direction first to see why this condition is necessary. Okay. It turns out that we use the same kind of coloring. Some large prime P. So this is the same technique that we're going to use. Right? So let me start with the lemma. Okay, let J and K be positive integers. And C1, C2, Cj be G to the K be vectors, such that C1 is not a linear combination over Q, so their coefficients are rational numbers, have the possibly empty set. But yeah, I mean, I allow, this means that J could be 1, C2, C3. Yeah, so this is not in the span of them. Then there exists a finite set F of primes such that for any prime P not in F, and any non-negative integer m, the vector P to the m times C1 is not a linear combination. Of C2 up to Cj modulo P. Oh, modulo P to the m. So this is a similar idea, but we still want to do it with the modulo something. Okay, so that's why I didn't use the terminology span, I want to use the linear combination with the coefficients, integer coefficients. Okay. Let's see why this is true. Since C1 is not in the span over Q of C2, C3, Cj, right? So there exists a vector u in g to the k. Should I say g to the k? Q to the k. At this time, q to the k, such that u is orthogonal to all of them. C2 dot u is C3 dot u and Cj dot u are all 0, but C1 dot u is non-zero. All right. By multiplying a big integer, we may assume u is an integer vector. Let f be the set of all primes p such that p divide u times u dot c1. Okay. Now, suppose p is a prime and m is a non-negative integer such that p to the m times c1 is a linear combination of c2, c3 up to cj modulo p to the m plus 1. All right. Yeah, so this is kind of like exceptional prime, like how this, we want to say that such a prime, number of such a prime is finite and belongs to F. So what does that mean? So P to the M times C1 is equal to A1, no, A2 C2 plus A3 C3 up to AJ CJ modulo P to the M plus 1. Right? Now we take a dot product on both sides. C1 dot u is equal to A2 C2 dot u, A3 C3 dot u, AJ CJ dot u. Now all these things are 0. That's construction. U is chosen to be orthogonal to C2 to CJ. So this means that PM times C1 dot u is 0 modulo P to the M plus 1. Alright? Yes. But now I can divide P to the M. So what you have is C1 dot u is 0 modulo P. So P divides C1 dot u. So P is in F. Okay? So that means any such exceptional primes are in the set F, but set of all primes dividing u dot C1 is finite. So that's why there are only finite remaining such prime, that other than that, p to the m times C1 is never a linear combination of C2 to Cj modulo p to the m plus 1. Now let's prove the forward direction of Rados theorem. So let A be a matrix with n columns, so that Ax is 0 is regular on set of positive integers. So for two disjoint subsets ij of n, if I is non-empty, then either sum of the Ci in I, well, one of the two things, right? It's a linear combination over Q over vectors in Cj, where J is in J, or, right, or what's going to happen? By applying previous lemma, so take this vector as one of the C1. Then by the previous lemma, if it's not a linear combination, then there are only finite many primes. Right? So there exists a finite set Fij of primes such that for any prime p not in Fij and any non-negative integers m, the vector p to them sum of the Ci is not a linear combination of vectors in J modulo p to the m plus 1, right? So whenever I take two subsets I and J, one of these two things happen. Now let F be the union of all Fij over all pairs Ij where Fij is defined. Okay, so that's still F is finite. Yeah, by the previous, this is by the previous lemma. So F is finite. Now let chi be the a base P coloring, and let's choose P not in F. Since F is finite, there's a prime outside of F. Okay. So what is base B coloring? Let me remind you. So the chi of integer m is a modular p when p to the l divide m, or I mean I should say m is p to the l times a, and a is not divisible by p. All right, so this is number between from 1 to p minus 1. So suppose that oops, this one x1 x2 xn is a monochromatic solution. Let Li be the integer such that xi is p to the Li times Li divides xi, but not Li, p to the Li. But p to the Li plus 1 does not divide xi. So this is maximum integer that divides, so that p to the power divides xi. So since chi of xi, let's say chi of x1, chi of x2, let's say all of them are equal to a, then this is equal to a, we have chi of xi is equal to p to the Li times a modular p to the Li plus 1. All right. Now, by rearranging, we may assume L1, L2. So let's rearrange the orderings so that we have the smallest number L1 in the first, and then continue. No, not T, it's Ln. Now, some of them are equal, some of them are not. So let B1, B2, BT be the integers such that I just said these two are equal. Okay, and let I be the set of indices such that bj is such that lj is bi. Right? So for instance, if we have if L is like 1 1, if L so for instance, if L is 1 1 2 2 2 3, then I1 is gonna be 1 2, I2 is gonna be 3, I4 no no 3 4 5, and I mean this could be 7, right? I3 is 6. Right, now you may already have guessed like what we're gonna do. We know that sum of xi ci is 0, right? And then for each m from 1 up to t, let's look at this. From 1 up to m minus 1, we have still xi. So yeah, let me write this way. So I can write this sum as from 1 up to t, and then for each one I look at the I, and then I add the c xj cj. This is 0. It's the same thing. Now from this sum I do this, and then now from m to t I have again xj cj is 0. Now all of these things are divisible by what, p to the li, no, p to the lm, right? So if I take a modular p, no, modular p to the lm plus 1, what's going to end up is from 1 up to m minus 1, we don't touch anything here, but from here, if I becomes m plus 1, then this is going to be, this xj will be 0 modulo p to the lm plus 1. So the only thing that remains is when I is equal to m. Right. Now, and xj here, the xj is equal to p to the lm times a modular p to the lm plus 1. So what we end up is, oh wait, do I have an lm? No, not lm. It's bm. Let me fix the notation. So this is bm. Okay. Right, and therefore what we end up is this. A times p to the bm times sum of cj is 0 modular p to the bm plus 1. Now, there is an integer, a tilde, such that a times a tilde is 1 modular p. Yeah, of course, a is non-zero. So let's multiply that. Then p to the bm sum of cj is equal to minus a tilde sum and xj cj. Modular p to the bm plus 1. Okay. Now, p is not enough. This is how we chose it. And this is a linear combination of them. What does that mean? We know from the previous lemma, right? This is, we know that this conclusion doesn't hold. It is a linear combination. Okay. So that means, well, by the previous lemma, this vector is a linear combination over Q of vectors Cj where J is in I and I is less than M. Right? So this means that A satisfies the columns condition. Okay? So that's the proof that we need the columns condition. All right, let me cut this video here, and I will do the second part, the different direction, backward direction, in the next video.